Okay, so what I have up here is, all right, let me back up a second. Okay, so this particular textbook, the TRO textbook, has separated material in chapter 2 and 3 in a way that I've never seen before. And that could be a good thing. In my opinion, it's not quite right. It's sort of strange. They go through element names, symbols, atomic structure, ionic structure, ion charges, the periodic table, and then they introduce mass, moles, molecules. And then they start with chapter 3 with nomenclature and then finish out percent composition empirical formula. I've never seen a textbook separate material that way. And it just doesn't kind of seem like it flows correctly. So if you opened up my courses and you thought, gosh, why is chapter 2 and 3, together? What I'm going to try to do today is I'm going to go through the part in the chapter 2 notes that's on the credit quiz 2. And then I'm going to show you in the notes, okay, the rest of it we're going to save for Tuesday because that's going to be on credit quiz 3. And then the same thing, we're going to go through chapter 3 notes and only cover what is on the credit quiz 2. And then on Tuesday, we'll finish it and go through what the content is for credit quiz 3. Basically, credit quiz 2, and you'll see this with the practice quizzes. The practice quizzes will tell you what's on the credit quiz, but the practice quizzes are all about atomic structure, ion charges, family names, and then nomenclature. And nomenclature is a beast. If you remember doing this in intro chem, nomenclature is a very big topic. And we're going to try to get through all of that today. Then the credit quiz 3 is all the math. It's the mass, moles, molecules, percent composition, empirical formula. And we're going to do all of that on Tuesday. So I'm sorry, I don't mean for it to be confusing. I just didn't feel like it flowed very well. And then also it was very imbalanced. Chapter 2 is really small. Chapter 3 is a lot bigger. So that's sort of the method for the madness. So hopefully this makes sense. But today's Zoom session is going to cover the content that's on the credit quiz 2. So when I post it later today, you'll know, okay. And I try to also do that with the notes. I have my short videos, the sections, like the segments on all the chapter notes. I put on there, this is on credit quiz 2 in the description box. This is on credit quiz 3. So hopefully it's very clear. If you have any questions on it, please let me know. But basically the big thing for this upcoming quiz for credit quiz 2 is nomenclature. Nomenclature is huge. So we got to go through that today. Atomic structure, family names on the periodic table. So quite a bit to cover today. So I'm going to go ahead and get started. The credit quiz, as I mentioned on Tuesday, you always have a week to do them. So we're meeting today. Obviously it's Thursday. So Thursday next week at midnight is when credit quiz 2 is due. I try to give a week to cover the content. I know we're moving a little bit faster in the summer, but I still try to give a week. And then I did post my homework answer key for chapter 1. And then I noticed this morning I hadn't done that for chapter 2 or 3. So I will do that probably tomorrow morning. My scanner is not working, so I have to go to my friend's house to use their scanner until I can get a new scanner because I'm not on campus. But anyway, so the homework answer key for chapter 2, 3, and 4, I think those are the only 3 left I have to post. I've got them. I just have to scan and post them. I'll do that tomorrow. Okay, so that was already a lot of information, but I'm going to go ahead and get started. I'm starting with the chapter 2 notes. I had sent an email out about a half hour ago that if you like printing out the notes ahead of time, we need chapter 2 and chapter 3 today. I'll take a break when we're done with chapter 2 in case you need to go print out chapter 3. And the other thing that you might want to have available if you have it, or if you don't already have it, you need the periodic table. You don't need it, but you might want to have it. Okay, chapter 2. All right, so I started with a quote from Democritus, 400 BC, right? Nothing exists except atoms and empty space. Everything else is opinion. I just think that's kind of funny. So chemistry is a language the way I kind of think about it, it is a foreign language. So chemistry, I always say it's sort of challenging because it's a lot of math, but there's like this foreign language aspect to it. So we start with the alphabet, right? Those are our element names and symbols. And you do need to memorize, not all of them, because that would be, we don't need to do that for Chem 1. And there's a couple of ways that you can test yourself on the element names and symbols. The first thing is if you go into that chapter 2, 3 folder, you've got a list of element names and symbols. So you could make flashcards if you like, and just read them. Most of them I think are pretty intuitive, first letter, second letter, that kind of thing, like lithium is Li. Some of them might be a little bit harder. If you look at the list, the classical name, if I gave it, it's only to help you understand where the symbol came from, but you do not need to know the classical name. So mercury is Hg. We're not going to worry about hydrogyrum, which actually means liquid silver. So that makes sense. But anyway, so I only gave you the classic name just so you could figure out why it was called, why it's Hg. Otherwise, that doesn't make sense. But you don't have to know the classical name, just the common or current name. So element names and symbols. The other way you could quiz yourself is if you look at my periodic table, you'll notice that some of the elements don't have the name listed, but yet some of them do. So one thing you could do is you could go through your periodic table, and anything that doesn't have the name listed, you should know what it is. So you could go through and be like, okay, H, hydrogen, lithium, sodium, magnesium, potassium, calcium, scandium, you don't need to know, titanium, right? And so that might be a way to kind of just quickly quiz yourself and say, okay, which one of these do I know? Which ones of these am I not sure about? Maybe highlight the ones that you're not 100% sure. And then you know which flashcards to make. So you don't have to make 55 flashcards. You only have to make maybe a few. Okay, so that's the first thing. There's a little bit of discussion about law of definite proportions and law of multiple proportions. Definite, right? Definite. So like every water molecule is an oxygen center with 2 hydrogens attached, right? So H2O. Multiple proportions is that you can take 2 elements and bond them together in different ratios to get 2 different substances. So we just talked about how water is H2O, hydrogen peroxide is H2O2. So that kind of makes sense. Definite meaning just that one compound that is the definite structure. Multiple proportions meaning there's multiple options for those 2 or more elements to come together to make a compound. So carbon monoxide, carbon dioxide is another example. So atomic theory, what I always love about atomic theory is that the atomic theory we have now, our atomic structure, is not what we started with. So Dalton came along 1800s. And actually, the first thing here, he kind of borrowed from Democritus, which was that all matter is composed of atoms. And atoms is I think it's Greek, it's from atomos, that's a Greek word, and it means indivisible. So there's some fundamental indivisible particle that makes up all matter, and we're going to call those atoms. And that atoms of a given element will have different properties or characteristics than the atoms of another element. So like all silver atoms look the same, all mercury atoms look the same, but silver and mercury atoms look different, right? That's all that's saying. And compounds are formed when atoms of 2 different elements come together and bond. So like carbon monoxide, carbon dioxide, and the fixed proportion, that's the definite proportion that we just talked about. Like every water molecule is H2O. And a chemical reaction involves the rearrangement of atoms. All right, the charges we will get to, and there will be some I need you to know. Yes, so the question was in the chat box, do we need to know the charges of all the elements? Not all of them, but certainly ones that are in specific families. And we're going to look at that when we get to the periodic table in just a little bit. So our nuclear model, at the time that it was first sort of theorized, we knew positive and negative particles. And so the kind of the original theory was, because we understand that positives and negatives attract, it was called the bread pudding or the raisin pudding model. And that sort of, or plum pudding, I've seen all 3, is that you have a plus next to a minus, next to a plus, next to a minus, next to a plus, next to a minus. In a way that's very intuitive. That makes perfect sense. And then Rutherford came along and threw all of that out the window. With his experimentation, he found, in fact, all of the positive charges in the center of the atom and all the negative is outside of that. So this is a different theory than what we started with. And we talked about theories on Tuesday that they can only be disproven, right? Not proven. So our first atomic theory was disproven by Rutherford. So protons, right? I usually abbreviate these P with a positive charge. If you were wondering, I think I probably should have mentioned that. Oops, it froze. My camera likes to do that sometimes. So I gotta just pause it real quick and then start back over. But if you were looking at that and thinking, what is that? That's what I mean. That's P positive proton, right? So P for proton, I always put the plus sign there because it is a positive particle. It is one of the heavy particles, and I put heavy in quotation marks because it's, like 10 to the negative 24 grams of P. So not very heavy, but compared to an electron, it's heavy. And it's always found in the center of the atom, which of course we call the nucleus. The neutrons are also found in the nucleus, and a lot of times I abbreviate those N with a 0 because they have no charge. Also, again, one of the heavy particles, and they're found in the nucleus. So basically for the atom, almost all of the mass is in that center nucleus. The electrons are outside the nucleus. Those are negative particles. So I abbreviate those E with a negative sign. And in terms of mass, these are considered the light particles, or relatively no mass, although that's obviously not true, but they are 2,000 times lighter than a proton and a neutron. So over 99.9% of the mass of the atom is in the nucleus, with those two heavy particles, the protons and the neutrons. So if we think about an atomic structure, atoms by definition are always neutral. If they're not neutral, they're called an ion. So atoms are always neutral. And what that means is the positive particles, the protons, are going to be equal in count to the negative particles, the electrons. All right. And so that's sort of our fundamental first theory about atomic structure, is that in our center nucleus, we've got our positives and our neutrals, right? Our protons and our neutrons, and then our negatives are outside of that, our electrons. So that is our first thing that we want to look at here. Now, what we learned with Dalton's theory, like we talked about, is that all silver atoms look the same, although we didn't know isotopes at the time. So that's not perfectly true, but we understand the point. There are some things about all silver atoms that are always going to be the same. And silver and mercury atoms look different. All right, so that's what we got to talk about next. So when we look at our periodic table, right, we have numbers. And I like this periodic table because we only have two. We don't have to worry about a bunch of other numbers. So let's see, we're talking about silver, Ag from argentum. The number on top is the atomic number, so 47. Number on the bottom is the mass number. You know, I wish at this point there would be just one master periodic table, sort of simplify it. Every element symbol, atomic number on the top, mass number on the bottom. For these mass numbers on the bottom, I typically go with just 2 decimal places rather than, so just had to pause it again. Didn't have this happen on Tuesday, so today's going to be our lucky day. So for zinc, 65.41, for copper, 63.55. I've always gone 2 decimal places with those mass numbers, but we'll talk about that more when we get into the chapter 3 content. Anyway, so this is what we're going to use for today. We're going to write some things on it. So the atomic number that's on top of the element symbol, that's going to give us our number of protons. So like what we were talking about with Dalton's atomic theory, all silver atoms look the same in that they all have 47 protons in the nucleus. All mercury atoms look the same in that they all have 80 protons in the nucleus. But the silver and the mercury look different, right? That atomic number is element specific. If you change the atomic number, you've changed the element. So if we had 48 protons, it's cadmium, right? So those numbers are always linked to that element symbol. So we know, looking at our periodic table, the proton number is never in question. We know if it's zinc, there's 30 protons. So that number is very straightforward. The number of neutrons we have to get by difference. Now we talked about the 2 heavy particles, right? The protons and neutrons. That makes sense that that would be the mass number. Because, right, that the mass, right, 99.9% of the mass are the protons and the neutrons. So what we do is we take that mass number and we subtract out the protons. If the mass number represents protons and neutrons, then let's take out the protons and we'll figure out what our neutron number is. So that's what we do to find our number of neutrons. Now your number of neutrons, it has to be a whole number. You can't have 0.5 neutrons. You either have a neutron or you don't, right? It doesn't come in fractions. So what we'll see is when we go to find out our number of neutrons, when we take the mass number from the periodic table, we're just going to round it to the nearest whole number. So for example, copper, if we're using 63.55, we'd round that to 64, right? So we'll practice that here in a minute. And like we talked about on the previous page, if we're looking at an atom, right, protons positive and electrons negative have to cancel out. They have to be equal in order to get a charge of 0. So your electrons are going to be equal to protons as long as we're talking about an atom. Again, that'll change when we get to an ion. All right. So to kind of sum up what we have so far, there's a couple of different ways of writing what's called an isotope notation. Now the isotope, which we'll look at more when we get to the chapter 3 content, when we actually look at the math behind getting these mass numbers. When we look at the mass number in the periodic table, right, we talked about how a neutron, you can't have 0.5 neutrons. So what this mass number is a weighted average of all the naturally occurring isotopes. So Dalton's theory kind of failed on this one, because again, we didn't know neutrons then, we didn't know isotopes. So if I pick up a sample of copper, yes, all of those copper atoms have 29 protons, but the number of neutron can actually vary. And some of the copper will be present in a certain isotope with a certain number of neutrons. And then another part of that copper will be a different isotope with a different number of neutrons. And if I take a weighted average of all of those isotopes, this is where we get that mass number. And that's why they're not whole numbers. All right. So when we write isotope notation, froze again. Okay, isotope notation, we can do a couple of different. So first thing on here is this notation where we have the element symbol. So I just put E for element and then A and Z. And A here is the mass number. That tripped me up a little. I was like, why is it A for mass number? And Z is the atomic number. That seems backwards to me, but you'll see how it's easy to keep it straight. So if we're looking at 10, 10 is from stannum. And that is SN. So again, when you look at your list, right, you only have to know 10. You don't need to know stannum, right? So for 10, our symbol is SN. So we have our element symbol. Now, when we look at 10 on the periodic table, we've got number 50 above it, right? So we know that the atomic number is 50. All right, and then the mass number below it, it says 118.71. All right, so let me write that down before I forget it. And then we'll talk about how we're going to do this isotope notation. Okay, so the first thing is the number, again, that's always fixed is that atomic number. And again, the atomic number is our number of protons. So when we look at our isotope notation, I know the A and the Z, I was like, why is A mass number? But it doesn't really matter. The Z, right, the atomic number, we write that one low. And honestly, I always felt like that was a little redundant, because 10 is always 50 and 50 is always 10. So why are we writing both numbers? So this is not my preferred isotope notation, but it's one of the ones in the curriculum. So we got to talk about it. Now the mass number up top, we could use the one from the periodic table, but in this question, we're saying that there are specifically 66 neutrons. So we're going to use that information to come up with our mass number. So instead of using the periodic table, we're going to use the information that was given to us. So mass number is our number of protons, which in this case is 50, added to our number of neutrons, which according to the question is 66. So when I add those two together, I get a mass number of 116, right? And so again, the mass number on the periodic table is just a weighted average of all the possible isotopes of 10. So this is a specific isotope that we're looking at. With 66 neutrons, add that to the 50 protons, we have a total of 116 particles in the nucleus. So that is one way to write an isotope. So specifically, again, I always thought the 50 was redundant. So the way I always like to do it, because I don't know, it seems to make more sense, is that you write the symbol and then you just write the mass number. Well, right, because that, right, we talked about how the 50 is redundant. So really the mass number is the only part that can fluctuate. So why not just identify that? And also you'll see it with the name 10116. All right, so either way, those are two ways of sort of expressing a specific isotope. All right, so if we look at the next example, kind of going in a different direction, we've got chromium 52. CR is chromium, which is from chroma, which means colored, because there are a lot of times very beautiful colored compounds. And the mass number for this isotope is 52. Remember, the 24 is never in question, because if I look at my periodic table, chromium is always going to be 24. All right. So we've got chromium 52. And again, I wrote it that way here because I kind of like that way better. We're going to look at protons, electrons, and neutrons in this particular isotope. So we talked about how the proton number is the easy one. That's the atomic number. So we know that our number of protons for this chromium is going to be 24. All right. So that one is easy. Then the next one that I'm asking for is the number of electrons. And it's going to be equal to the number of protons because we're talking about an atom of chromium. If we talk about an ion of chromium, that's going to change. But for this example, we're starting with atoms. So we know if there's 24 positive particles, there has to be 24 negative particles. And that's why overall the charge is 0. Then the last particle is the number of neutrons. And for this one, we're going to take our mass number and minus the atomic number. And we were told that, again, we could go to the periodic table and pull the mass number from here, but we won't do that here because we're told specifically to use isotope 52. So we're going to take our 52 minus 24, and we get 28 for our number of neutrons. All right. So that's how we get protons, neutrons, and electrons for different isotopes of an element. And kind of just tying back to what we learned with Dalton's law, we know that every 10 atom looks different from every chromium atom, right? But not all 10 atoms look exactly the same, like Dalton first hypothesized. But again, we didn't know neutron structure yet or isotopes. Now, we talked about atoms always being neutral, right? And so you have to make sure and be careful when the question is asking you how many protons, neutrons, and electrons in this atom, or if it says in this ion. So make sure you pay really close attention to that. If it's an ion, the charge is no longer zero. It's carrying a charge. It could be positive, it could be negative. We'll talk about how we predict that in just a little bit. And if you kind of think about the structure of the atom, the nucleus, we say that's pretty much set. We don't learn about changes in the nucleus until we talk about radioactivity in Chem 2. So for now, we assume that the nucleus doesn't change. The protons and the neutrons, that stays the same. The electrons, however, outside the nucleus, they can come and go. And we have actually some pretty good ways of predicting exactly how many will come and go, because we understand at this point that the noble gases are incredibly stable, and there's something really good about that. And all the other elements, if they could, they would try to feel exactly like that noble gas feels, just nice and relaxed and stable. So ions. All right, first thing is I'm now going to go to my periodic table. All right, and when you look at your periodic table, I'm going to draw the metalloid stair step. So it goes between boron and aluminum. We go over, then down between aluminum and silicon, over between silicon and germanium, down between germanium and arsenic, over between arsenic and antimony, down between antimony and tellurium, and then down, or sorry, over between tellurium and polonium. So we've got this like nice, easy to see stair step. And that is our boundary that separates metals and nonmetals. Now, everything to the left, which is most of our periodic table, these are all metals. There is an exception here. And if you look at your periodic table, I'm going to slide this over here really quick, is we've got all the way at the top, we've got hydrogen. All right. And hydrogen is an exception here. It is a nonmetal. And, you know, what we know about metals, right? They're usually solids at room temperature. A lot of them are gray. They're all in that sort of gray silver color family. Unless they're ions and compounds, then that changes. But just as a metal, as the element, they're good conductors of energy. You know, we learn different things about metals. Nonmetals are, if we look over to the right of the stair step, like the noble gases, oxygen, nitrogen, right? These are gases at room temperature. If they are solids like sulfur and phosphorus, they're powdery. They don't look like metallic solids at all. All right, so over here, we've got nonmetals. So there's obviously much different characteristics of metals and nonmetals, but the other sort of big difference between the two is what type of ions they form. So metals will always lose electrons to form ions. And if you lose negative particles, you become a positive ion. And that term that we use for that is cation. And I always remember the T as my plus sign. So made it easy to remember the terminology that the T means positive. I don't know, at least that's what my brain said. So if you think about it, the nucleus hasn't changed. We still have the same number of protons, but if we're losing those negative particles outside the nucleus, now that means we're going to have more positives than we do negatives, and that's why overall we have a positive charge. So if you lose electrons, you become positive. Nonmetals are going to be the opposite, right? They're going to gain electrons, and they are going to become negative ions, and we call those anions. And to me, that always looked like it stood for a negative ion, right? Doesn't it, like a negative ion? I don't know. But again, that's just kind of what my brain thought about it. All right, so how many do they gain? How many do they lose? We have to talk a little bit more about other things before we get there. But this was the next thing in the notes, right? Cations are positive ions. That belongs to metals. Anions are negative ions, and that belongs to nonmetals. All right, so if we go back to where we were in the notes, right, the cation, remember the T is the plus sign. All right, and then up at the top, we've got the negative, the anions, right, because they gain electrons. So periodic table developed first by Mendeleev. I watched a documentary about him. He was pretty interesting. So he was a Russian scientist, and he was a professor. And he was trying to kind of organize what we knew about the elements at the time. There's only about 55. And if you imagine, right, no internet, no organized information where you can find all in one place. A lot of the elements at this point they went back centuries, right? Discovery like gold and silver, lead. So like ancient discovered centuries before. So there's those. And then there's more recent discoveries of like the alkali metals by Sir Humphrey Davy and some of the alkaline earth metals. Anyway, there's this scattering of all these elements. So he compiled all the information and he organized it by atomic mass. And he found that it's really interesting. Like he had all the halogens together, for example. So I remember this because this always stood out to me. Like he had fluorine, chlorine, bromine, iodine, and then he left a spot for here. He called it eka-iodine. And then of course, later they found this element, they discovered it and they call it acetine. So he was the first person, the father of the periodic table. And it changed obviously, but he was the first person to sort of put everything together. Now the metalloids, we had talked about that stair step, right? And so we talked about metals being to the left and non-metals being to the right and how they have very different characteristics. So it makes sense that when you're on that boundary, you have kind of special elements that can maybe act somewhat like a metal in some cases, but then also like a non-metal in other cases, right? It kind of depends on what they're partnered up with. And so these are your metalloids. And basically it's everything above or below the stair step except for aluminum. All right, aluminum, we know aluminum. Aluminum's it's a metal, right? It reminds us of a metal. But all of those others are metalloids. All right, and the example I always use here, if it helps, great. If not, just remember your metalloids, is silicon. Because if you're familiar with baking, you have like a lot of bakeware now will be silicone bakeware. And that's sort of not what we use typically, right? When you're trying to conduct energy from your oven to your food, you use something metallic, right? So all of our baking pans, right, they're always metallic, but silicone came along and it's this nice flexible rubbery material, right? Lightweight and, not at all what we would think about for a metal. So you wouldn't think of it being a good conductor of energy, but yet it is, right? So silicone is always the one I kind of use as like, that's how you remember. No worry, David. Thank you. Okay, so these are your metalloids. Then we have our metals versus our non-metals. Let me go back to the notes. I'll just make sure I cover everything. Okay. And then the main group elements versus the transition elements. A lot of times the terminology will be the representative elements versus the transition elements. This book likes to say the main group elements. Basically what we've got in the middle of our periodic table. So right between my fingers, if I go scandium to zinc, and then I go down in that block, that sort of shrunken block right in the middle of the periodic table. These are the transition metals. And we know they're metals because they're to the right of the stair step, but they're called the transition metals. Right. And so it does stop right at that zinc border, right? And at the scandium border, right? So we've got a lot of transition elements for sure. Everything else, we talk about those being the representative elements or the main group elements. Okay, so the question about the metalloids, the only ones that are going to come up, because I have seen different books do these metalloids a little bit differently. The only ones that we're going to have to worry about, because they're on our element names and symbols list, so you want to make sure you remember them, are boron, silicon, arsenic, and antimony. Those are really the four that we'll use in this class, because like remember the name isn't there, so those are the ones we want to know the name of. Tellurium, polonium, we don't ever really use that much, and same with germanium. Not to play favorites or anything, but those are just the four that we have on our element names and symbols. So those are the ones really I want you to remember as being metalloids. All right, good question. So we've got our transition elements in the middle. Our main group elements then, or our representative elements, would be our 6 columns over on the right, and our two columns over here on the left. Now, this first group right here, all right, not hydrogen, but lithium, sodium, potassium, rubidium, cesium. Let's hope there we go. These right here, these are called your alkali metals. And we know they're metals, right? Because they're to the left of the stair step. So those are your alkali metals. Alkali meaning base. These metals, when you add them to water, they turn water into hydroxide, which is base. So that's where that name comes from. The group 2 metals next door, they do the same type of reaction. We'll learn those when we start writing chemical equations. So like magnesium, calcium, strontium. But what I remember is these are group 2, so they have 2 names. So these are alkaline earth metals. All right, and again, hydrogen is just the exception here, that it's a non-metal, but everything else in that first column is an alkali metal. And then in that second column, we've got an alkaline earth metal. All right, and then additional family names that we want to remember. If we scoot over to the right side, I don't want to move too quickly. So we have our alkali metals, we have our alkaline earth metals, we've got a lot of transition metals. When we come over to the right side, we already identified those metalloids. That means we've got a few elements here that are not special. They don't have any special name, they are just metals. So aluminum, tin, lead, bismuth, right? Those are those names that we need to know. Those are just metals, nothing special, just metals. Then at the very end, a lot of people know this one. These are the noble gases like helium, neon, argon, krypton, xenon, right, radon. And I will put a picture of this. Yes, I will scan this too. In fact, I think there's one already there, but if not, I will put this one in. Then right next to that, we've got fluorine, chlorine, bromine, iodine. These are called your halogens. And those are the only ones I typically use. But there are other names, but those are the ones I typically like to stick with. All right, so if we look at ions, we had this question earlier, how do you know what charges do you have to remember, right? So there's going to be some elements that when we look at them on the periodic table and where they're placed, we know, okay, that's how many ions, or that's the ion charge they're going to carry because they've either lost this many electrons or gained. All right, so there are other elements though that we don't have that. First thing is, what we talked about was noble gases have what everybody's looking for. They have, it's like a stability switch is kind of what I think about, like the way the electrons are organized. Something happens when you get to this noble gas number of electrons where a stability switch clicks on and the atom is incredibly stable, doesn't like to ionize at all. So basically everything's trying to get to that magic electron number. Not everything though, transition elements are different. So really we're just talking about the main group elements. So halogens, right? We know that they're nonmetals. We know that they're going to gain electrons. How many are they going to gain? All right. Fluorine has 9 electrons as an atom, but really wants to look like helium. So it wants to have an extra one. It wants to go to 10. Chlorine has 17, but really wants to look like argon, right? So it always wants to pick up 1. Bromine 35 really wants 36. So the halogens always pick up 1 electron when they ionize, which means they're always going to carry a -1 charge. So that's the first one we can easily predict. The oxygen family, 8 electrons here. We know that nonmetals, again, they gain electrons. How many do they gain? Oxygen wants to pick up 2. Sulfur wants to pick up 2. Selenium wants to pick up 2, right? We're trying to get to that noble gas number. So oxygen family, -2 charge. All right, nitrogen family gets a little bit trickier, only in the sense that like nitrogen and phosphorus, we expect probably -3. Arsenic, antimony, like we talked about, those are metalloids. They're a little bit more unpredictable because it's going to depend on what they're partnered with. And then down at the bottom, we've got bismuth, which is a metal. So instead of negative, it should be positive. So for here, I'm going to put -3. But what I want you to kind of keep in mind is that's really only true, easily predictable for nitrogen and phosphorus. Arsenic, a lot of the times, yes, but again, it'll depend on what it's partnered with, but absolutely not for bismuth. Bismuth is a metal, so instead of negative, it's got to be positive, right? So the -3 here is just really those 3 elements. The carbon family, again, kind of the same issue. I don't like putting -4 up here because that would only be true for carbon as a nonmetal. in an ionic compound too. Carbon a lot of times doesn't like to do a lot of ionic compounds. It's usually more covalent. But anyway, silicon, germanium, harder to predict. And then tin and lead, instead of negative, they're always going to be positive. So I usually just go with noble gases, rate 0, and then -1, -2, -3. I don't put anything for the carbon or the boron family personally. All right, now the metals, again, underneath the metalloid stair step, these always are positive charge because they're metals as ions, but a little bit harder to predict. But the one here that is easy to predict is aluminum. Aluminum is always a +3 charge. It always wants to lose 3 electrons. Because it's a metal, we know it's going to lose. It has 13 electrons, but it really wants to get to 10, right? That magic number 10. So it loses 3. Zinc, a little bit harder here to fully capture until we get into electron configuration. So for now, I hate to say this, you got to take my word for it. Zinc likes to always be a +2 charge, and silver, same problem, but we're going to just take my word for it, always likes to be a +1 charge. So what I want you to remember is there's this nice diagonal right here that kind of makes this easy to remember. So you just want to remember 3, 2, 1. Aluminum always a +3, zinc always +2, silver always +1. So 3, 2, 1. Now the rest of the transition metals, I typically don't assign a charge. There are some under here that also have certain charge, like cadmium is also always a +2, but then mercury is +1 or +2. Yeah, the chalcogens, I don't think we need to know this. So Mike, sorry, I just saw your question. I always kind of stick with your noble gases and your halogens, and I don't go into the chalcogens, but that's just me personally. So don't worry about those. All right, so there we go. All right, so the rest of the transition metals, we won't worry about memorizing any charges. So the only thing we have left to talk about are the alkali and the alkaline earth metals. All right, so alkali metals, again, wanting to look like a noble gas and knowing that they lose electrons. So lithium, actually, I'm going to do this. Well, no, I can't. So lithium has 11 electrons as an atom, but really, once again, to look like neon with 10. So we're losing 1 electron always with the alkali metals. So alkali metals are always a +1 charge as ions. The alkaline earth metals, these are always going to be +2. And if you're wondering, okay, well, why is hydrogen over here? It's because it is like alkali metals and that it often always, well, not often and always, that's, anyway, often is a +1 ion, but not always. So, but hydrogen is often +1 as an ion. So that's kind of why it's over there with the alkali metals. The very first periodic table I always used when I started teaching had hydrogen right in the middle, which I thought really was actually the proper place for it because it doesn't really belong. Doesn't belong over here with the metals. It kind of belongs in its own special little category. All right, so we talked about our family names. Now let's talk about what that ion charge means in terms of the electron count. So this is going back to where we were in the chapter 2 notes. All right, it says how many electrons would be present in the ions of sodium, magnesium, nitrogen, oxygen, and fluorine. All right, so first we've got sodium. It's an alkali metal. We're just going to talk about the family names here, repeat that information. And we know that as an ion, it's going to carry a +1 charge. All right, and so that +1 means that it has lost 1 electron, right? +1 means you've lost a negative particle. So the atom, we're going to talk about the atoms first. The sodium atom, if we look at the periodic table, it would have 11 protons and 11 electrons. All right, so 11 electrons for the atom. If it's lost an electron, that means it now has 10 electrons. So when I look at my periodic table, remember, we're thinking everything is trying to look like a noble gas structure, and that would match the electron structure of the neon atom. So that seems to make sense, right? So sodium +1 ends up with 10 electrons. If we look at magnesium next, all right, it is an alkaline earth metal, and I probably need to save some space here. So let me just go grab the number of electrons. In the atom, protons would be 12, which means electrons would be 12. So there would be 12 electrons here. We know as an ion, magnesium, alkaline earth metal, becomes a +2 charge. which means it's lost 2 electrons. All right, and then that means it would have 10 electrons. So again, it's going to match that structure of neon. Now, nitrogen is atomic number 7. So as an atom, 7 protons, 7 electrons. And we said that as an ion, nitrogen should carry a -3 charge. That's what we assigned for that. So -3 charge. Instead now of losing electrons, that means it has gained 3 electrons because it's now -3. So we have 3 extra negative particles. So we went from 7 adding 3 to now having 10 electrons. All right, next one we've got is oxygen, which is atomic number 8. And we said on our periodic table, oxygen should carry a -2 charge. So went from 8 electrons, picking up 2 electrons. So again, now it has 10 electrons, so you can see where we're going here. Last one is fluorine, which is atomic number 9. And as an ion, fluoride is a -1 charge. It has gained 1 electron, which again means 10 electrons. So that's one of the kind of fundamental assumptions of the main group elements, is that when they ionize, they're trying to get that noble gas feeling, which is a nice, stable, happy feeling. I'm assuming they're happy. And all of those 5 that I gave you, the sodium ion, the magnesium, nitride, oxide, fluoride, they all end up looking like neon. So there's a term that you give ions that have the same electron structure. So I'm going to write this up above. The sodium ion and the magnesium ion and the nitride ion and the oxide ion and the fluoride ion, they all look like neon, right? They all end up with that, and the equals is just the electron equals, right? The electron count. And that term that we give for ions that have the same electron structure is we say that they are isoelectronic. All right, iso, right? That's our prefix to say something looks the same. Iso means the same. So isoelectronic, same electron structure. So these 5 ions that we just looked at have a same electron structure, 10 electrons, as neon. And so they're all called isoelectronic, same electron structure. All right, so for the chapter 2 notes, that's what you want to worry about for credit quiz 2. Right, so we talked about atomic structure, we looked at our family names, the charges that we can expect based on position on the table, what that does to the electron count. The next page in the notes where it starts, and you can make a little note here, we're going to come back to this on Tuesday. So the next page on the notes is talking about atomic mass, and we can put a little note on that. That's going to be where we pick up on Tuesday, and that'll be content for credit quiz 3. So again, anything that has a lot of math to it, like mass, moles, molecules, what we're going to talk about next week with our mass spectrometers, that's all credit quiz 3. So what we've done for chapter 2 so far is all for the credit quiz 2. All right. And so when you go into my courses again, when you log in, the videos for the chapter 2 notes, they're separated. And I've said, okay, this is the content for credit quiz 2, and then this is the content for credit quiz 3. All right, so hopefully it's really clear, but definitely let me know if anything is not clear. Now what I'm going to do is kind of switch and start talking about chapter 3 notes. And again, we're going to start with material here first that's on credit quiz 2. All right, and again, not to be confusing, I didn't like the way the material was separated. I thought it was really weird to introduce mass, moles, molecules in chapter 2, but then not do anything with it in chapter 3. I thought, wait, what? And then it's also weird to present protons, neutrons, electrons, atoms, and ions, but then not do nomenclature until a different chapter. Just personal preference. I guess I've been doing this 20 years. I kind of feel like, I don't know. That's just me. So we talked about how elements want to either gain or lose electrons because they want to end up looking like a noble gas. That noble gas goal can be found by creating ions, which is what we just looked at, or it can be found through bonding. And there's different types of bonds. So that's the first thing that is covered in chapter 3. We have ionic bonds, which makes sense. Those are ions, right? So those are the ions that are held together by electrostatic forces, which are the positive and negative, which attract, right? Highly attractive forces. And if it's a positive and a negative, that means it's going to be a metal and a non-metal, right? Because we know that the metals are positive and the non-metals are negative. We just looked at that. And in this case, in an ionic bond, there is electrons that have been lost by the metal and electrons that have been gained by the non-metal. So there's a full-on transfer of electrons. But what we'll find out as we go further into the semester later is that not all metals and non-metals, let me back up. You don't always have to have bonds between metals and non-metals, right? Sometimes, like we saw with water, right? Hydrogen is a non-metal, oxygen is a non-metal. So this maybe isn't quite right. Maybe it is, maybe it isn't. And then like carbon monoxide, carbon is a non-metal, oxygen is a non-metal. So that's going to be a different kind of bond. When two non-metals come together, those are called covalent bonds. And what happens here that's different is we've got carbon and oxygen, both non-metals, both prefer to gain electrons. So nobody's going to just lose, right? So instead, what happens is they share electrons. That's the difference. Now, the molecular, ionic, and formula unit, this is like splitting hairs to me. Technically, an ionic bond is made up of ions, right? Cations and anions. And technically, we call those compounds, we call them formula units, all right? Whereas if it's a compound, if it's covalent, that's what I'm going to say, non-metal and non-metal, covalent, then what happens here is we call those molecules. So if you have seen or you are about to see a distinction between molecule and formula units, that's all that is. And to me, it's splitting hairs. I don't think we need to be that picky. But molecule technically is for a compound, a covalent compound, and a formula unit is typically what we call an ionic, but it's the same thing. So like sodium chloride, 2 or more elements bonded together. In chapter 1, we learned that's called a compound, right? But technically it's called the formula unit because it's ionic. But I typically don't use formula units because again, I think it's being a little bit too picky. Now for the test, when you are taking your test, you are going to have your periodic table. It's going to be this exact periodic table without all of my writing on it. So it's another reason why I like kind of starting with this, so you know exactly what periodic table you can expect to see on the test. It will be this periodic table, just not with all my writing on it, right? So that'll be available for you for the test. So I saw that picture or question come in. The molecular formula, empirical and molecular formula, that's going to come at the end of chapter 3. So we're not going to worry about that until Tuesday. Now, there are 7 elements that they don't exist individually. They exist diatomically. So for example, if we talk about iron, iron is just single, right? Just Fe, that's it. So elemental iron, we just write the element symbol, that's it. Silver, Ag, right? Chromium, like we saw earlier, Cr, no big deal. But there are 7 elements that are not stable singularly. They occur diatomically. Di, of course, meaning 2. And when I was learning this, I look for patterns to make things easy to remember, because I think I mentioned I don't really love memorizing stuff. The thing I saw on the periodic table was it made a 7. There are 7 of them. So you've got hydrogen, and you kind of go over nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So that's how I remembered it. But then as I started teaching, I think there must have been a teacher somewhere along the way that taught their students that you could remember it using Hofbrinkel. And then I thought, well, that works pretty well too. Now they're not in any kind of order here like this is, but these are the 7 diatomic elements. So for example, like when we talk about oxygen gas, it's not just O, it's O2. Nitrogen gas, elemental nitrogen, not just N, not stable, it's actually N2. All of our halogens are on that list: fluorine, chlorine, bromine, and iodine. And then hydrogen, same thing. It's not hydrogen gas, it's just H, it's H2. So this is when we're just talking about an element though, right? If we're talking about an ion, like we saw earlier, ions are singular unless they're polyatomic. Okay, so if we're talking about oxygen, the element, in its elemental form, no charge, we're talking about O2. If we're talking about oxygen, the ion with a -2 charge, now it's singular. It's not going to have that diatomic, that 2 subscript. So that's kind of that can be tricky at times to know. All right, in this case, does it have the subscript or does it not have the subscript? So the big thing here is when we're talking about those 7 elements, Hofbrinkel, when they're bonds, right? So this is alone as an element, and there is no charge here. That's the other big thing. That's when they're going to be diatomic. All right, so hydrogen by itself, no charge, is H2. All right, chlorine by itself, no charge, is Cl2. When we talk about the ion, chloride ion is just Cl, -1, no subscript of 2. Oxide, no subscript of 2, singular, -2 charge. So ions, these are single. If they're not single, they're going to be polyatomic ions, and that'll be something we talk about here in probably about 15 minutes. Okay, so first example here. We've got 5 things. We want to look at these as elements, diatomic elements, molecular compound, ionic compound, or polyatomic. All right, so gold, the symbol there, this is one that sometimes is tricky for students. They like to confuse it with silver. If you know, and this probably is not helpful, Au is from aurum, that's the classical name, and aurum means shining dawn. So that's where that name came from. Then you'll be like, okay, yeah, aurum is gold. So I don't think that's probably very helpful, but maybe you'll remember it. So gold is Au. That's just an element. It's not one of our 7 diatomic elements. So this is just an atomic element, singular element. All right, silver oxide, which is Ag2O. When I know that's obviously a compound, but is that going to be a covalent molecular compound or an ionic compound? And what I know from looking at my periodic table is that silver is a metal, so it should be a positive ion. Oxygen is a nonmetal, which means it should become a negative ion. We talked about metal and nonmetal making ionic compounds. So that one, the silver oxide, should be an ionic compound. Carbon monoxide, what's different here is now we've got carbon, which is a nonmetal, with oxygen, which is a nonmetal. And that was the example I used. When you have 2 nonmetals, you have a covalent. I like to first specify that it's covalent, but technically, according to the list, it is a molecular compound. Right, and just to reiterate what we saw back in chapter 1, right, if it's a single element versus 2 or more elements bonded together, right, 2 or more elements bonded together means you've got a compound. Ionic, because metal and nonmetal come together. Covalent or molecular, because 2 nonmetals come together. All right, oxygen, like we just talked about, as O2 is going to be a diatomic element. Now, another thing that happens here, we haven't quite gotten it, but we will in a minute when we get to the nomenclature, is oxygen is the O2. That's what we just looked at in our example. The singular oxygen with the -2 charge actually has a different name. This is referred to as oxide. All right, so they are distinguished by name as well. So if we say oxygen, technically we're referring to O2, no charge, diatomic element. Whereas if we're talking about the ion of oxygen, we call it oxide, and that actually helps us know which one we're looking at. The last one on the list here is something called nitrate, and it is NO3 -1, which means there's a nitrogen bonded to 3 oxygens, and there's an extra electron here. And that is something called a polyatomic ion. Makes sense? Poly, meaning many, right? Meaning many atoms that come together and carry a charge, right? So the nitrate here is a polyatomic ion. And we're going to become very familiar with those here in a little bit. All right, so just looking at kind of our 5 different types of elements and compounds that we have, right, in polyatomic ions. All right, ionic compounds. Ionic compounds, also called salts. Salt is like a generic term to a chemist. That means an ionic compound. And again, we talked about that being a positive cation and a negative anion, which means a metal and a nonmetal, right? And they come together, and we always want the simplest whole number ratio to balance out the charges. So if sodium is +1 and oxygen is -2, we want to balance out those charges by putting 2 sodiums with an oxygen. So Na2O. We always want the simplest way to balance out those charges. Rather than putting 4 sodiums and 2 oxygens together, we're going to just do 2 sodiums and 1 oxygen. So we always want the simplest ratio. That's number 1. Now, the negative part here and the positive, technically, they don't necessarily have to be singular ions. They could also be polyatomic ions, like the nitrate that we were just looking at. All right, but we're going to get to that more here in just a little bit. The next thing on this page is the charges that we already went over in chapter 2. See why I think chapter 2 and 3 are organized in a weird way, right? So we talked about the alkali metals always being +1, alkaline earth metals +2. On that diagonal, aluminum, zinc, and silver, 3, 2, 1. Our halogens always -1, right? And the ending changes to "ide." So this is another example, bromine, just like oxygen, one of our diatomics is Br2. But when we talk about the ion, which is singular, Br -1, we call it bromide, just like we called O -2 oxide. Oxygen, sulfur, selenium, we expect -2 charge. And then nitrogen, phosphorus, and arsenic, we're expecting a -3 charge. All right, so when we make an ionic compound, we're going to put a positive and a negative together. There are binary and non-binary compounds. All right, binary means that there's only going to be 2. So if it's ionic, that means you're going to, you're going to have a single metal cation and a single non-metal anion. So there's only going to be 2 elements in the compound. And what we always do here is we make the ending IDE for the nonmetal. Now, the problem we're going to have is when we put these compounds together, there are going to be some metals where we know what the charge is just by looking at the periodic table. So like we know sodium is always a +1, never anything else. But there's other metals like chromium where we don't know the charge by looking at the table. Chromium can be a +2, a +3, or a +6. That's hard to get from that position, right? So we're going to have more work with those transition metals, but we're not quite there yet. So what we do with an ionic compound is we name the ions. That seems pretty simple, right? So with a binary ionic compound, you have a metal and a nonmetal. The nonmetal is always going to get the IDE ending. All right. The metal, we just name it. So like if we see Na, we just say sodium. If we see calcium, or sorry, Ca, we say calcium. But there's an asterisk here. We're going to have to ask a little question. Is it type 1 or is it a type 2 metal? All right. So what does that mean? All right, a type 1 metal means there's only one possible charge. And those are the ones we've memorized. So the alkali metals, the alkaline earth metals, aluminum, zinc, and silver. Those charges we know because they're only that possible charge. There's only one possible charge. So if it is a type 1 metal, then all we have to do is name the metal. But if it is a type 2 metal, meaning it has more than one possible charge. So that's what's up here in the notes. If the metal has more than one possible charge, right? And those are the ones we're not going to memorize all the possibilities. So that's all the rest of the transition elements, like the chromium example I just gave you. Sorry, I'm pointing to manganese and iron. Chromium, the tin, lead, bismuth, right? All of these other metals, for those type 2 metals, now what we have to do is we have to name the metal and in parentheses indicate the charge that that metal is carrying, and we use a Roman numeral to do that. So that makes kind of, I think, perfect sense in my opinion. I'm just going to go off script here a little bit. If I asked you, okay, give me the formula for copper chloride versus sodium chloride. All right, so chloride we know is Cl negative. It's a halogen, so we know -1 charge. The sodium we know is Na, group 1 metal, +1 charge. Copper from cuprum we know is Cu, but when I go to my periodic table, I look at it and I say, I don't know the charge on copper because the periodic table, I didn't have to memorize that, right? I don't know what that is. So there's not enough information with just saying copper chloride. I can't assume it's +1 because chloride's -1. You can't do that. We need more information here. So because copper has more than one possible charge, it can either be a +1 or a +2. In parentheses, we need a Roman numeral that tells us what it is. So if I say copper 1, then I know, okay, this is copper 1. The other option is copper 2. And of course, then I know it's copper with a +2 charge. And now that I have that information, I know how those ions are going to come together. All right, so that's why the type 2 metals are going to require more work for us. All right, so let's get practicing just naming first. All right, so the first one here is we have CaBr2. All right, so Ca is calcium. Then I'm going to go to my periodic table, find out the position. All right, calcium, alkaline earth metal. I know it's always +2, so I don't need to say it's +2 because it's always a 2. It would be redundant. No Roman numeral is needed here because when I say calcium, it automatically means +2. Then the second part here is the bromine, and the non-metal, we change the ending to IDE. So calcium bromide is all we need to say there. I know a lot of students want to look at that and say, well, don't you have to say dibromide because there's 2 here? And the answer is no, because you know that calcium is always a 2, you know bromine is always a 1. So that's the only way for those 2 ions to come together. So to say dibromide is redundant because there's no tribromide with calcium, right? So you just have to say that this is calcium with bromide and that's it. That's all you need. The same is true with the next one, right? Lithium, Li, is an alkali metal and it is always a +1 charge. And sulfur in the oxygen family is always a -2 charge. So sulfur we say is now sulfide. So we change that ending to IDE. And we know that we don't have to say dilithium because we know there's no other way for those 2 charges to balance out. If sulfur is -2, we need 2 lithiums to balance, but we don't have to say dilithium because again, there's no trilithium, right? It's just lithium sulfide. That's it. That's all we got to do. So when it is a type 1 metal, and I'll write this here. If it's a type 1 metal, which again is your alkali metals, your alkaline earth metals, and then your aluminum, which is always a 3, your zinc, which is always a 2, and your silver, which is always a 1, just name the metal. That's all we got to do. So again, with an ionic compound, your job is to name the ions. So with the non-metal ions, they always push the ide ending. So like oxygen becomes oxide, bromine becomes bromide. But if the metal part, the cation part, the type 1 metal, you just have to name the metal. You don't change the ending. You don't need a Roman numeral. Don't need a prefix. You just say lithium. That's it. So lithium sulfide, Li2S. All right, more examples on the next page. Okay, now we're going to get to something a little bit different. We've got FeBr2. All right, so Fe from ferrum we know is iron. Iron, periodic table, don't know the charge. So that means it's type 2. There's 2 or more possible charges here. So we're going to need a Roman numeral here to identify the charge on the iron. But let's finish it out first. We saw this earlier. Bromine is bromide. So that part is no different. If it's a type 1 or type 2 metal, it doesn't affect how we name the non-metal. The non-metal still pushes the IDE ending. Now the iron, the Roman numeral. The only way to know iron is to know bromine, right? So type 2 metals are transition metals like iron, but also you want to remember most of your type 2 metals are the transition metals except for silver and zinc. But then we've got a few metals down here in the underneath the metalloid stair step. So tin, lead, bismuth, those are also type 2 metals. So these would also need the Roman numeral, right? So if we start with bromine, all right, bromine as an ion we know is -1, right? So that's why it's called bromide, right? Bromine is Br2 with no charge. Br -1 is bromide. All right, -1. Now there are 2 of those in the compound, right? Because it has that subscript of 2 on it. So really I've got an overall -2 charge. So that's my anion side. And I usually kind of split it. Then on the positive side, we've got iron. And we know overall the charge on the compound has to go to 0 because that compounds are like atoms, neutral. So if I have a -2 on the negative side, I'm going to have a +2 on the cation side. And since I only have one iron, it has to be a +2 charge to get that charge to balance out. So this has to be iron 2 bromide. I'm reading the chat here really quick. Okay, so the 2 here, that is confusing now that I think about it. All right, if we're talking about bromine, bromine by itself is Br2. There's no charge, and not that you need to know this, it's a liquid at room temperature, right? So there's my bromine. If we're talking about bromide, right? Bromide is Br-1. It's the ion of bromine, right? So bromine has now picked up an electron, and now we call it bromide, and it's Br-1. The reason why we know that this is bromide and not bromine, even though it looks like it would be bromine because it's got the subscript of 2, is because it's not alone. It's in a compound. And whenever we have a metal and a non-metal, we know it's an ionic compound. So we know that here we have the ion of bromine, which is bromide, because it's partnered with a positive iron. So that's the difference. When you have Br2 alone, then we call it bromine. It would be completely by itself. But if it's Br2 in a compound, really it's Br with a -1 charge. Now, the reason why there are 2 here is because it's partnered with iron that has a +2 charge. So to make those charges come together and go to 0, since iron is a +2, I need 2 bromines to balance it out. So it's got to be FeBr2. So when we name our ionic compounds with type 2 metals, we start with Fe, iron. Then we say, okay, we need a Roman numeral for iron because we don't know the charge. There's more than one possibility. The non-metal always gets the "ide" ending. And the Roman numeral, you can kind of do an easy, well, I mean, it's not always easy, but we try. There's a crisscross that'll work here. So when we look at Fe, and I'm going to leave some space, Br2. First, we start with the non-metal, right? Because we know that charge. We know from the periodic table that the halogen should be -1. So we start with that. If the charge on the non-metal is the subscript for the metal, absolute value, right? So don't worry about the negative. If that is correct, then the opposite will always be true. So we know that since the charge on bromine, the 1, is the subscript on the iron, which is technically a 1, then that means the subscript on the bromine, the 2, is going to be the charge on the iron. There's a crisscross that always happens here. So sometimes that helps you quickly identify the charge on the metal. So this is iron 2 bromide, right? Iron is carrying a +2 charge. So next one we've got is CuI2. All right, so Cu from cuprum is copper. It's a transition metal. We don't know the charge on the copper, so we're going to find the Roman numeral, but we'll come back to that because we got to figure out the non-metal part first. Iodine is going to become iodide. All right, and so when we look at our charges here, I like to break things up. We've got copper, don't know the charge, and then we've got iodide, which is -1, just like bromine. It's in the same halogen family. When I look at my formula, there are 2 iodines in the compound, right? It's got a subscript of 2 multiplied by 2. So -1 times 2 means overall we have a -2 charge. So to balance, we're going to have a +2 charge. And since there's only 1 copper here, that means that copper has to be +2 to cancel out. So just like with the iron, this is going to be copper 2 iodide. Again, the crisscross, right? The charge on the iodine is technically the subscript on the copper. So the subscript on the iodine is technically the charge on the copper. All right, so there's that crisscross that sometimes will help you. So copper 2 iodide. Now on the next one, we've got copper again, and this is why we need the Roman numeral. In this case, copper is not a +2 charge. In this case, it's partnered with sulfur or sulfide, technically, right? Because the non-metal always gets the IDE ending. And what I know here is sulfur in the oxygen family is a -2 charge. And there's only 1 of them in the compound, so overall -2 charge. With the copper, I have 2 of them in the compound, right? It's got a subscript of 2. And I know my -2 needs to be balanced by a +2 total. But if there's 2 coppers in the compound, that would mean each one is a +1 charge. But you see how that crisscross is working for us again here, right? The charge on the nonmetal, the 2, is the subscript on the copper, 2. That means the subscript on the sulfur, which is a 1, is the charge on the copper, which is a 1. But if you kind of go through this piece by piece, start with your nonmetal. We know the charge on sulfur, it's -2. There's only 1 of them in the compound, so total -2 charge from the nonmetal side. That means we have to balance that with a +2 total from the positive side. But if there's 2 coppers present, that would mean each one has to be carrying a +1 charge. So this is copper, 1 sulfide. Now, if your previous chemistry teacher had you learn the classical naming system, I'm sorry. No, I had to learn it too, but it's just, it seems why, like why make it more difficult? We already have enough on our plate. That's kind of how I look at it. And the stock system, which is what we're using here, works perfectly well. The classical naming system would have you remember that copper has 2 possible charges. It's either a +1 or a +2, like we identified in these 2 examples. Then it would have you remember that the lower charge gets the us ending and the higher charge gets an ic ending. And then on top of that, you have to use the classical name, which isn't copper, but it's cuprum. So copper 1 is called cuprous. Copper 2 is called cupric. All right. I don't use the classical system. I think the stock system is much easier, more straightforward. Why not? Right. And it works just as well. So if you were like, wait a minute, I think I remember cupric and cuprous. Great, you can use it if you want. I just don't. I like the stock system better. All right. The last one on here, we've got CO, which we know is cobalt. All right, we'll come back. Cobalt, when we look at our periodic table, right? Another transition metal. So we know we're going to need a Roman numeral. We'll come back. And then oxygen, we know is going to be called oxide. Then if I look at my charges, right? Let's see if we can do this like a quick one. Right, oxygen, just like sulfur, -2 charge. That's what you always have to start with because that's the only part you know, right? Cobalt, we don't know. If the charge on the oxygen, the 2, is the subscript on the cobalt, which it is, it's a 2, then that means the subscript on the oxygen, which is a 3, is going to be the charge on the cobalt. So this should be cobalt 3 oxide. Now, if you prefer to do it kind of the step-by-step longer way, and there is absolutely nothing wrong with that, we're going to come over here. We've got CO2 and then O3. And I'm just going to kind of separate it. Oxygen is -2. -2 times 3 means I have a -6 total. So I have to balance with a +6 on the positive side. 2 cobalts times what charge, I'll just call it X, is going to equal +6. So 2 times what is a +6. That would mean cobalt has to be a +3. And that's what we want to put in parentheses is the charge on each individual cobalt, not the total +6 for both cobalts, but just cobalt 3 oxide. All right, so cobalt 3 oxide. All right, I'm going to just finish out binary nomenclature and then we're going to take a break. So I just got to finish out this page and we can all get a drink, take a breath, whatever it is we got to do. All right, now going in the opposite direction. All right, potassium we know is K from kalium. It's an alkali metal, so we know it's a +1 charge. Sulfide means sulfur, and we know oxygen family -2 charge. And my screen froze again. This seems to, it didn't happen at all at Tuesday. It's great. All right, so when we make a compound, the charges have to come together to go to 0. And again, going back to what we talked about, we always want the simplest ratio to make those charges go to 0. Now, the crisscross method is something that will work. Just know that if it can be simplified, you need to simplify it. And I'll show you an example down below where we're going to have to simplify it. But basically what will happen here is that charge on the potassium is going to become the subscript on the sulfur, right? And the charge on the sulfur is going to become the subscript on the potassium. Basically what we're saying is if potassium is a +1, we need 2 of those to get a +2 total to balance a -2 on the sulfur. So when we write our formula, we're going to have to make it K2S. And so again, going back to the rules and nomenclature, that's why we didn't need a prefix. We don't need a Roman numeral because saying potassium sulfide was everything we needed to get that formula to come together. That means it's got to be K2S. All right, lithium, also an alkali metal, +1 charge, oxygen, just like sulfur, -2 charge. It's in the same family. And again, you can do that crisscross. We're going to need 1 oxygen, but 2 lithiums to make this work. So it should be Li2O. And again, if you think it through, lithium's a +1. I need 2 of them to get a +2 total, and that'll balance the -2 on the oxygen. All right, aluminum fluoride. All right, we know is +3. Right, and I just want to highlight that really quickly because that's one of the sort of special ones on the diagonal, right? Aluminum's always a 3. Fluoride, while I'm here, halogen, -1. So we know fluoride means F -1. And if you want to do the crisscross, we're going to need 1 aluminum and 3 fluorides. So AlF3. All right, it's much easier going this way. Chromium 3. All right, so now remember, chromium 3 tells you that this is chromium 3, right? And not to be redundant, but it means it's chromium with a +3 charge. A lot of times I'll have students when they get these type 2 compounds with the Roman numeral, I do this in my intro chem lab. They'll come up and they'll be like, well, wait, chromium, I don't know the charge on chromium. I'm like, you're right. That's what that's for, right? The Roman numeral is there to tell you it's a 3. Oxide, again, we know oxygen, -2. So crisscrossing here, we're going to need 2 chromiums to get a +6 and 3 oxygens to get a -6. So formula here will be Cr2O3. All right. Iron 2 sulfide, iron Fe +2 charge, partnered with sulfur -2 charge. So again, you always want the simplest way for those 2 ions to come together. And when you look at that, it kind of makes sense. +2 -2, we should end up with just FeS, right? That cancels out the charges. But if you do kind of start with doing that and you came up with Fe2S2, just look at that and simplify it. Say, wait a minute, 2 and 2, I can make that 1 to 1. All right, last one on the page, lithium. We saw this one earlier, +1 charge. Nitrogen is a -3 charge as an ion, right? So nitride is referring to N -3. And if I crisscross, I'm going to need 3 nitrogens to get a +3 and only 1 nitrogen to get a -3. So Li3N. All right. So binary nomenclature, just to sort of summarize, what I'll do is in the break, I'm going to add to my periodic table here, and I'm going to highlight, because I got to go grab my highlighter, that if we've memorized the charge, right, the +1 alkali metals, the +2 alkaline earth metals, and then this silver, zinc, and aluminum, we don't need a Roman numeral. But for all of the other metals, we're going to have to include a Roman numeral to identify the charge, right? But that's a good place for me to take a little bit of a break. It's 12:33, so let's come back at like 12:38, do a 5-minute break. And then if anybody has any questions for me during the break, let me know. But otherwise, I'm going to take 5 minutes to just kind of give everybody a little bit of a break. Okay, it's 12:38. I'm gonna go ahead and pick up. I saw in the chat about posting the periodic table. I'm so sorry. I thought I had done that. So just really quick, I'm gonna share my screen just for a couple of things I wanted to point out. First thing is, upon request, between the chapter 1 and chapter 2, 3 folder, I posted the periodic table. So if you want just a lot of students like to do that. They like to kind of just start with a blank periodic table and highlight things and as they're studying. So there's one here if you need it. It's the same one that I use for the test, right? So there's your periodic table if you want it over here. And the other thing was, question came up about the periodic table we're doing today. So if you scroll down, I'm sorry, I probably did that too quickly. We're in the chapter 2, 3 folder. And if you scroll down about halfway, maybe a little bit further than halfway, a couple of things here. The element names and symbols to memorize, that's here. So again, it's not all elements on the periodic table. It's just that list that I looked at earlier. If you want the complete list, that's there for you, but you don't need it. And then there's also polyatomic ions to memorize. And I'll show you that as we get into that, because that's the next section of nomenclature we're going to do. And there's also a lot of videos here for nomenclature. So nomenclature is a beast. right? You're learning like a whole foreign language part of chemistry in one chapter. So there's a lot here. I try to give a lot of content, not to overwhelm you, just to give you a lot of examples. So there's a lot of videos that I posted there for nomenclature. And then if you go back up here, right above the element names and symbols list, there's a nomenclature flowchart and a periodic table. This nomenclature flowchart, when I was learning nomenclature, I had to sort of do this for myself. I had to say, okay, how's all this working again? So with nomenclature, if you go in understanding that there are 3 different systems, there's a system for ionic compounds, there's a system for covalent, and then there's a system for acids. And the first element in the compound tells you what system you're in, then it's not so bad. Otherwise, it sort of seems kind of random. But if you can see that pattern first, then it's like, okay, I've got an ionic compound. My job is to name the ions. I've got a covalent compound. My job is to use prefixes to say how many. If it's an acid, right? So there's different things we have to go through. So this system here, I don't know, I know it's my handwriting, so it's not great, but if it helps, this is how I approach nomenclature, or this is how I try to, organize it in my head when I was learning it. So if your compound starts with a metal, we know that if it is an ionic compound, the positive ion always comes first, which means the metal will always appear first. Now, to throw a little bit of a exception, because there's always exceptions in chemistry, a little bit of an exception here, there is one positive polyatomic ion, and because it's positive, it would appear first in the compound. And that is NH4 plus, which is ammonium. And we'll look at that in just a little bit when we get to our list of polyatomics. So in an ionic compound, your job is to name the metal and the nonmetal, or sorry, the cation and the anion. What we've done so far is we've named the metal and the nonmetal. But as we get further into the next section, we're going to now look at, okay, what if we have polyatomic ions? The simple thing is, it sounds, some of these compounds look quite terrible, but you really only have 2 pieces you have to name. You have to name the cation and the anion. If your cation is a type 1 metal, like your alkali metal, your alkaline earth metal, aluminum, zinc, or silver, we just name the metal. If it's ammonium, we just say ammonium, because the charge is not in question. If it's a type 2 metal like iron, cobalt, right, those ones that we saw in the last set of examples, then you have to name the metal and use that Roman numeral to identify the charge on the metal in that particular compound. So like iron 2 or cobalt 3, right? That's what that Roman numeral was for. The anion portion of this, we've got 2 options. Now, so far, we've only looked at the anion being a non-metal. And that's when we push the "ide" ending. So we did sulfide, oxide, nitride, chloride. But the other possibility here is that we have a polyatomic anion. And those are going to be harder because it's going to require some memorization, right? And the big thing here is we don't use prefixes, right? Because they're usually, for this section, they're going to be redundant, right? Now, the second section of compounds that we have, let me scroll back up, is when your first element is a non-metal, right? So now we're starting our compound with like carbon or sulfur or phosphorus, something to the right of the metalloid stair step. That means we're going to have a non-metal and a non-metal, which when we talked about this earlier, those are 2 elements that want to gain electrons so nobody loses. So it's not ionic. Instead, they share electrons. And we'll see this as we go through the semester. A lot of times they can come together with that law of multiple proportions and make different compounds, like we know carbon monoxide and carbon dioxide. So what we do here is we don't worry about ion charges because there aren't any. So that's kind of refreshing. Instead, all we have to do is we have to say, okay, this compound has 2 oxygens, so we say dioxide. Or it has 6 chlorines, so we say hexachloride. So we have 12 prefixes here. Honestly, we don't really use undeca and dodeca very much. I used to watch 30 Rock, when that was in its heyday, and I remember she was taking in this thing, she was taking birth control that you only had to take once a year, and they called it dodecacil. And I was like, oh, that was clever, because dodeca means 12. But anyway, the prefixes mono, di, tri, tetra, those are all pretty straightforward. Sometimes tetra students miss, but I'm a lot older. So tetra, I always thought of tetras, which are typically like 4-sided objects that you try to fit. I don't know, I used to like that game. Penta, we're more familiar with, right? Pentagon, that means 5. Hexa, just remember the X is your 6, right? Hexa means 6. Hepta, 7. Octa, like octagon, octopus, that makes sense. That's going to be 8. Nona, I always thought double N, that makes sense, that's 9. Deca, like decade, that would mean 10. And then there's undeca and dodeca for 11 and 12. Now what you do here, and we'll see this when we get to the section in the notes, nope, stop, is when you look at these, we only have 2 elements to name. The first nonmetal, we name it as is, and we only use a prefix if there's more than 1. So like when we had CO2, we just said carbon. We didn't say monocarbon. There's only 1 carbon, so we just say carbon. Now the second nonmetal, we again see that IDE ending. And on the second nonmetal, we use a prefix no matter what. So like carbon dioxide, if it were CO, it would be carbon monoxide. Now, another example here is N2O, 2 nitrogens would be dinitrogen. And I'm sorry, it got cut off on the scan. 1 oxygen would be monoxide. But these were always my favorite because I thought they were the simplest, right? They're easy. You just know your prefixes and you're good to go. The problem though is that if you think about your periodic table, we don't have a lot of nonmetals. So there's not going to be a lot of options for binary covalent compounds. And when they are non-binary, you get to learn a whole different system, and that's called organic. And that's coming, I'm sure, down the road for some of you. Now, the last type of compound we have is when we have hydrogen in front. And that has its own special system. If it's hydrogen in front, it's an acid. It is still technically an ionic compound, so we will still have to worry about charges. But the special thing about an acid is that the cation, the positive in front, is always H+. The anion is going to have the same 2 options that we saw over here with ionic compounds. It can either be just a single nonmetal like chlorine, right, or chloride technically, or it could be one of those polyatomics. So if it's just a simple nonmetal with hydrogen, that means it's a binary acid. There's only 2 elements in the acid, H and a nonmetal. And these have a very specific name. They're always hydro blank ic acid, and the blank is filled in with the stem from the nonmetal. So like HCl is hydrochloric acid, HBr, hydrobromic acid. If it's hydrogen partnered with a polyatomic, these are going to be a little bit harder because you have to know the name on the polyatomic. And so you would know your polyatomic ions, they typically have 2 possible endings, ates and ites, like sulfate and sulfite. If the polyatomic ion ends in 8, we drop the 8, replace it with ic, and then add the word acid because it's an acid. All right, and we'll practice this in just a little bit. If the polyatomic ion ended in ite, we drop ite and replace it with us. So when I was learning this, I looked at this and remembered it 2 ways. I looked at it as alphabetical, A before I before O, that again, whatever makes it stick, right? The other thing you could do to remember is the I's don't go together, right? Ite and ic, that's not right. So I don't know, however you want to remember it is up to you. So that's the nomenclature system. You might want to have that at the ready while you're practicing your nomenclature. Why do I keep doing this? Okay, then I'm just trying to hit, there we go. And then if you go down further, there's my periodic table with some things highlighted, and we're going to go through more of this today too. Your type 1 versus your type 2, your charges, right? We're going to do more of that here in a little bit, right? So that's posted for you. I'm going to stop my share, go back to the notes. And I think, thank goodness I hit record when we came back. Any questions for me? Okay, so if we go back to the notes where we were, now what we're going to talk about is ionic compounds that are non-binary, right? So these are non-binary ionic compounds. All right, so what happens here now is it's weird. It says non-binary, but technically there are still only 2 pieces. There's a cation and an anion. That still is true. The problem though here is that the anion is going to be a polyatomic. All right, so now instead of just sulfur, which we would call sulfide, we're going to have sulfur in a polyatomic SO4, which we call sulfate, or SO3, which we call sulfite. And the only way we're going to know this, if we don't already, is by looking at the list of polyatomic ions. And that's what's posted in my courses. So I'm going to be jumping back and forth for this. So like, again, if we see a compound that has SO4 in it, we're going to know, oh, okay, we call that sulfate. It's not sulfide, right? It's sulfate. If it's SO3, then we say it's sulfite, right? So we're going to be going back and forth. Now you got to memorize that list. I know that seems daunting. But I have a Quizlet. Let me write myself a little note. I had made a Quizlet to help students memorize that. So let me post that as soon as we're done for today. That might help you just, if you're visual, right? It might help you just kind of scroll through that Quizlet, learn those polyatomic ions. It's basically flashcards. You just click on it and it turns, so you can learn them that way. I don't learn best that way. I learn best by writing something down. That's just me. So I'd have to make my own flashcards. If I write it down, I'm much more likely to remember it. I have more of like a photographic type memory rather than like, I don't know, maybe if that's true anymore. But anyway, you got to figure out what works for you. Non-binary ionic compounds, what's going to happen is your cation is still typically going to be that metal. We're still going to have to ask the question, do we need a Roman numeral, right? But now, instead of it just being partnered with a single non-metal, it's going to be partnered with a polyatomic. So we're going to see a different ending here. Instead of "ide," we're going to see "ates" and "ites" usually, all right? So some examples here for us to look at. We got KHCO3. Now, sometimes this type of compound confuses students because we know potassium is positive, but we also learned hydrogen is positive. So they're like, wait, is this two cations here? Like, how do I handle that? Your cation, unless it is ammonium, that's the only positive polyatomic ion we would ever have, right? Unless you see NH4, when you look at this compound, it's only the K that's the positive, right? So you pull that out. We're going to name the cation, and we know K is potassium. When we look at our periodic table, potassium is a group 1 alkali metal, which means we know that it's always a positive 1 charge, which means we don't need to put a Roman numeral. So potassium, that's it. The rest of this HCO3 is what we need to name as the anion. So we go to our list of polyatomics and we look for HCO3, right? It has a -1 charge, which makes sense. That balances the +1 on the potassium. When I name this, I actually have two options. I can either call it hydrogen carbonate or I can call it bicarbonate. You choose. I typically like in my face-to-face class to say hydrogen carbonate because it helps us kind of remember that there is carbonate by itself down here with a -2 charge. And if I put a hydrogen in front of it, the charge goes up by 1 because hydrogen's +1. And we still are calling it carbonate. We just now say it's hydrogen with carbonate. So that's why I typically like that. But I know it's a lot shorter and simpler to just say bicarbonate. So you choose, right? So potassium bicarbonate or hydrogen carbonate. Now the next one we've got Fe, and we know Fe is iron. And we by the way, the capitalization part, I always get asked about that because I'm a little bit not picky about that. When you're writing the name, capitalization to me doesn't matter. When you're writing the symbols, that's when the capitalization matters, right? It's got to be big F, little e in order for it to be iron. All right, but if you put little I or big I here, that's okay. That doesn't matter. All right, iron. We saw this earlier. Transition metal, we're going to have a Roman numeral. So we're going to come back to that. So it's just like we saw before. There's still two pieces here. It's a cation and an anion. It's just now the anion is this group. So I'm not going to just say phosphide. I have to figure out, well, what is PO4, right? So whoever got together and made the rules, they said PO4, it should be called phosphate, right? And yes, you need to memorize the polyatomic ions. So PO4 is called phosphate. All right, now phosphate is a -3 charge. When I look at this compound, we were talking about the crisscross earlier, and it can be a little tricky here because a lot of times students want to think there's 4 phosphates here, but that 4 is part of phosphate. So if you have a polyatomic ion and it's not in parentheses, that means there's only one of them there, right? There's just one PO4 group, and that group is called phosphate. There's only one iron here, right? And so to balance, that iron has to be a +3 charge. So this is iron 3 phosphate. Again, classical name would be ferric phosphate, but I like iron 3, it works better. Well, it doesn't work better, it just is easier. All right, magnesium, Mg. Alkaline earth metal, group 2, always a +2 charge, don't need a Roman numeral. Now what we see that's different here is I've got this H2PO4 thing in parentheses. That's my polyatomic ion. So I need to look at what H2PO4 is. So I look at my list of polyatomics H2PO4 carries a -1 charge, and it's called dihydrogen phosphate. All right, so that makes sense because phosphate was PO4. If I put 2 hydrogens in front of it, then that makes sense that this is going to be dihydrogen, right? 2 hydrogens with phosphate.
Is it dihydrogen because hydrogen is a nonmetal?
So the di versus like mono, is that what you're thinking?
Yeah.
So the polyatomic ions, like I know we said with ionic compounds, you don't use prefixes, and that's true, except when it's in the name of the polyatomic. So what we have here is like phosphate is PO4, HPO4 is hydrogen phosphate, and then if it's H2PO4, then we say dihydrogen phosphate. It's not ideal.
Do you mind giving me one more example of that?
Which one? Which one in particular?
Just another, like one where it would have a dihydrogen or like a different, like when we would use that system.
Okay, sure. So when we look at our list of polyatomics, most of the polyatomic ions will, if there's a hydrogen option, there's only going to be like SO4 is -2, it's called sulfate. And if I put an H in front of it, it's hydrogen sulfate. And when there's only a possibility of doing one H, then that's when you can use that bi instead of hydrogen. But in the case of the phosphate, because it's a -3, we can either put just one hydrogen in front of it and call it hydrogen phosphate, or we can put 2 hydrogens in front of it and now call it dihydrogen phosphate. And just that's why we don't have biphosphate. It's only because bi isn't really particular enough, because technically we can have 1 hydrogen or 2 hydrogens. So when you see the compound formula, because that 2 is there, that's why we know that this is the dihydrogen phosphate. If, for example, we had CaHPO4, Ca is calcium, and now because there's only 1 hydrogen, this is called hydrogen phosphate. I don't know, does that help?
It did. Thank you so much.
Yeah, you're welcome. And so that the name is just coming from the list on the polyatomic. And I agree, it's like it's not really ideal because we stress in ionic compounds, we don't use prefixes, but it's only with that polyatomic ion that we have that issue.
Where
Right,
are
so-
you using the 2 from the outside the parentheses or when we said dihydrogen?
Okay, good question. The reason why we're saying that it's dihydrogen is because of the 2 that's there. And so that's coming from the name on the list. So like, sorry, we got magnesium, which we took care of. And now I'm looking for this H2PO4. And when I look at that, H2PO4 is called dihydrogen phosphate. So that's why we're there. Now, that's a good question though. Why is there this 2, right? That 2 is because magnesium is a +2 charge and the dihydrogen phosphate only carries a -1 charge. So I shouldn't have used my red pen. I need the 2 here to balance out the charge on the magnesium. Not that that's the name of it. That's just balancing the charge. The name that di is coming from there. Does that help?
Yeah, that makes sense.
Okay, perfect. So now if we practice going in the opposite direction, we're going to have a name. We're going to come up with the formula. I always feel like this way is easier. At least it was for me. Ammonium is a special one. Like if you learn your element names and symbols, you're like, well, that's not an element name, right? That I know of. That is the only positive polyatomic ion we have. So ammonium means NH4+. So that's my cation. So again, in an ionic compound, you're just naming the cation and the anion. So that's the cation. The carbonate, what we want to recognize here is that our endings have changed. Before the break, when we were looking at binary compounds, we always saw IDE on all of those compounds. Now what we're seeing is a lot of 8s, and the other possibility will be ites, which we'll see in the next example. So when you always focus on the last 3 letters, if it's 8, we know it's not just carbon, it's going to be a polyatomic ion with carbon. So we're going to think about our list of polyatomics. We're going to go find carbonate. So when I look at my list, carbonate is CO3 -2. So I'm going to copy that over. Carbonate, CO3 -2. So there's my 2 ions that are in this compound. Now, when I put those two together, I'm going to do the same thing I did when it was binary. I have to balance the charges. So if you want, think about that crisscross. So I'm going to need 2 ammoniums to get a +2 and only 1 carbonate to get a -2. So because it's a polyatomic, we're going to have to put it in parentheses and then multiply it by 2. So there's my 2 ammoniums. And carbonate, because I only need 1 of them, I don't need to put it in parentheses. So I needed 2 ammoniums to get a +2 charge. So I say, okay, here's my ammonium times 2. And then carbonate, I only need 1 of them to get the -2 to balance out. So I just write CO3 because that's what carbonate is. The calcium hypochlorite, calcium, group 2, alkaline earth metal, always a +2 charge. Hypochlorite, I got to go look for that, right? It's not just chlorine, it's obviously something else. So when I look, I find hypochlorite, and so I'm going to copy this over. This is ClO with a -1 charge. So I have ClO -1 charge. So those are my 2 ions that are in this compound, calcium and hypochlorite. And again, I got to think about balancing charges. +2 - 1, least common multiples of 2. So I only need 1 calcium to get a +2, but I'm going to need 2 of the hypochlorites to get a -2. So we just crisscross it. So 1 calcium, so we can leave the 1 off. Polyatomic ions, so it's got to go in parentheses, and then we follow it with the 2. All right, so again, that 2, actually, let me do a highlighter. This 2 here, right, is not part of the polyatomic ion, it's part of the charge balance. And I think that's one of the hardest parts about learning these subscripts to begin with, because there are some, and we'll see this when we do equation writing, there are some subscripts that are part of the unit, and there are some subscripts that are just charge balance, and they serve a different purpose. When we say carbonate, we know it has to be CO3 because that's part of the unit. When we say hypochlorite, we just say ClO because that's the unit. The 2 here, though, is because I got to balance the charge on the calcium. And since hypochlorite is only a -1, I need 2 of those to make this compound come together and go to 0, right? If the hypochlorite is -1, now that 2 times -1 is -2, and that balances the +2, and that's how I get my charges to cancel out. So the subscripts can be problematic because there's 2 different purposes, right? One subscript is because it's part of the polyatomic. Another subscript is there because it's balancing a charge. All right, next one, last one, we got chromium 3 and then sulfate. And on my list of polyatomics, let me show you so you're not wondering where I got that from. Sulfate is SO4 -2. So I just copied that over. So there's my chromium 3, right? Chromium +3. And then sulfate is SO4 -2. So when I look at that, those charges obviously don't cancel out. If we crisscross, we're going to need 3 sulfates and 2 chromiums. So chromium gets a subscript of 2, and then sulfate gets a subscript of 3. Basically, if you look at your charges, 3 times 2, this would be a +6 total. And then 2 times 3, this would be a -6 total. And that's how we get the charges to go to 0. So again, the 2 and the 3 are charge balance subscripts, whereas the 4 is just part of the unit. So that's serves a different purpose. Now, there's a little bit in here. This is new from intro. We didn't talk about hydrates in intro chem. A hydrate means water, right? You're hydrated. So that's kind of what we think about. And so you'll see this come up a little bit. You've got an ionic compound, and then you've got water after it. And that's what makes it a hydrate, is the water, right? That makes sense. And what happens with the name of this is we still name the ionic compound the same, like this is magnesium sulfate. And all we do here is we use a prefix to say how many waters we have. So if it's 7, earlier we saw the prefix for 7 was hepta. So we would say magnesium sulfate and then 7 waters, so heptahydrate. All right, so that's what we do with a hydrate compound. Let me do another one down here at the bottom. Okay, so let's say I've got All right, CaCl2.2H2O. So Ca, calcium. All right, now going back to what we did before the break, this is just chlorine. This is a binary compound. So what we think here is instead of like the 8s and ites that we saw on this page, there's no other element here. This is just the calcium, which we already took care of, and then the chlorine. And we know chlorine will become chloride, right? Chloride always marks it as binary. Then the second part of this is that there are 2 waters. So to say 2, we use the prefix di and hydrate for the water. So that would be calcium chloride dihydrate for 2 waters. And what happens with this is a lot of ionic compounds, they have like a crystalline structure that's like, it looks like a box, right? And inside that box, water molecules like to get in there and hang out, and they're called hydrated. So there's water molecules inside the crystal structure. And so in this case, in each calcium chloride box, there's 2 water molecules that have snuck inside there. So we say that this is calcium chloride with 2 waters in it, so dihydrate. All right. So what was different than what we did before the break on this page is now all of these compounds are non-binary, more
Excuse
than
me.
2. Yeah, go ahead.
Sorry, I was just looking at a worksheet that I had from last semester. I may have wrote it wrong. Is the 2 underscore on chlorine ide or ite?
Okay, so that's a good question. If it is CaClO2, right, not to be too confusing, this is calcium
Sorry,
chloride.
I just answered my own question.
Okay,
Or
no,
you
you're fine.
answered it before I got it now.
Yeah, no, but I'm glad you asked because it's going to come up. So like there's 1 letter difference. Like I'm not going to sugarcoat this and not say nomenclature with chemistry is a little problematic. So I've got IDE versus ITE, right? The only thing that changed is 1 letter. So you have to be like super careful about this. That's why I'm glad you asked. If it's just a metal and a non-metal, right? There's only 2 elements here. We go with the IDE ending. If it's a metal and with a group of non-metals, right? That's where it's a polyatomic. And so now that name comes from my list. So when I go and I look, right, the calcium part doesn't change, but now I go and look for ClO2. And when I go and look and I find ClO2, not ClO3, not ClO, but ClO2, that's called chloride, right? And that's chloride. Now, also to be confusing, up here, we've got ClO with a 2 outside parentheses rather than no parentheses. So you have to be really careful about this. If it's just, let me use my pen. If it's just Cl, then we use IDE ending. If it's just ClO, right, inside the parentheses, then we say hypochlorite. If it is a ClO2, now that 2 is part of the unit, then we say chloride. So there's no doubt you have to be really careful with these. Like I'm glad you asked because you got to really kind of pay attention. Like where's the 2? What does it mean, right? So the 2 here is balancing the charge on the calcium. The 2 up here in the calcium hypochlorite is balancing the charge on the calcium. The 2 here, sorry, this technically should be with a parentheses followed by a 2. This is -1, this is +2. So again, those subscripts have 2 different purposes. Inside the parentheses, right, that's the polyatomic, the name is chloride. Outside the parentheses, it's because we're balancing the charge, all right? Now the name, why is it like hypochlorite? The system, this may or may not help. When you learn your polyatomic ions, what you'll notice is, and I'm going to do a separate video that I'll record later today and post it. When you learn your polyatomic ions, you're going to notice a lot of these either have an 8 or an ite, right? And what you'll notice is it's 1 oxygen different. So if you can remember the 8, you automatically know the ite. You just drop an O. So sulfate, SO4, sulfite, SO3. Charge stays the same, -2. Up here, we've got nitrate, nitrite, right? We had phosphate, phosphite. So that makes it a little bit easier with the memorizing. Just remember the ite has 1 less oxygen. With the halogens, there's actually, instead of just 2 options, there's 4. So we start ClO3, chlorate. So the O2 is the chloride. That keeps with what we had. but we can actually go one extra oxygen and one less oxygen from those two. So we borrow some prefixes, and I always think of like biology being hypo and hyper, right? Hyper means you have a lot of something. Hypo means you're low. So if I'm lowest in oxygen, I still have the "ite" ending for less oxygen, but now I say hypo, right? Low oxygen. If I'm really high in oxygen, I say hyper, but of course we gotta be different. We don't say hyper, we say per, and then 8 again, meaning more oxygen. So I think that's kind of where the naming came from, hyper and hypo. But it's just really coming from this list and memorizing it, but it might help you remember them better. The lowest amount of oxygen with the halogen is hypoite, hypochlorite. The most amount of oxygen is the perchlorate, hyperoxygen, so perchlorate. So I don't know if that helps or not, but I'll do a separate video on how to memorize those polyatomic ions. And that's just the nomenclature for polyatomics, right? Whoever made that up is, we can blame them for it. Okay, now molecular compounds. That was our last system we had to look for. Sorry, no, it's second to the last. We got to do acids next. We got 2 more to go. So this is the system that was in the middle. And we already saw the prefixes when we were naming the hydrate, the hepta, the di, right? So with molecular compounds, again, this is covalent compounds. This is when we have non-metal and non-metal. So what we see here is there will not be any ions to worry about, which is great. So we don't have to worry about charges. We simply have to know our prefixes and use those prefixes when we name the compound. So these were always my favorite. They're the easiest, right? Not to be lazy about it, but I like these. They're easy to remember. So we got formula for a compound that has 2 nitrogen atoms, so N2, and 4 fluorine, N2F4. So when I go to name it, I'm going to take my first element and name it as is, so nitrogen. And I'm going to say how many with a prefix as long as there's more than one. So I'm going to say here that this is 2 nitrogens, right? So dinitrogen. For the second element, I use a prefix no matter what. Since there are 4 fluorines here, I'm going to say tetra. And then that non-metal, the second one, always again gets that "ide" ending. So dinitrogen tetrafluoride. All right. Then I've got formula for tetraphosphorus. So P4, tetra meaning 4. Decasulfide. So sulfur, deca meaning 10. So P4S10. And then this one, to name it, S7O2, 7 sulfurs, we would say hepta sulfur. So remember, the first non-metal, you just name it as is. So sulfur, there's 7 of them, so we put the hepta prefix. And then the second non-metal, oxygen, becomes oxide, and we have 2 of them, so dioxide. So hepta, sulfur, dioxide. So those, again, those are my favorite. And there's more videos on covalent compounds if you want more examples, but I want to get through acids, and we only have 15 minutes left. So this material, there are some pretty long practice assignments to do, but they're helpful to really kind of spend the time on it, I think. And there are other videos, again, that you can look at for more examples. So when we name acids, this is our third and final type of compound. These are still going to be ionic. And so again, like what we talked about, if it's an acid, you're still going to have a cation. It's just the cation is always going to be H+. And then you're going to have an anion. And the anion can either be just a simple non-metal, negative, right? Like fluoride or oxide or sulfide, or it can be a polyatomic, like the sulfate that we saw, or the carbonate or phosphate, right? And so they're going to have to be distinguishable, right? If it's hydrogen with just chlorine, that needs to be distinguished from hydrogen with chlorine and oxygen, right? Like the chloride that we saw earlier. All right, so some examples here. If it's HI, right, then what I have here is the hydrogen with a non-metal, right? And this is a binary acid. So hydrogen and a non-metal means that it is a binary acid. If it's hydrogen with a polyatomic, that means it's non-binary. There's more than 2. In this case, I've got a binary acid, all right? And binary acids always have a very specific name. they always go hydroic acid, right? So binary acids always, always, always have that system of hydroic acid. The only thing we have to do is plug in the stem for iodine, which is IOD, right? That's the stem for iodine. So hydroiodic acid. Now on the next one, we've got HIO3, right? So this one's different. This is non-binary. Now I've got more than two. So what we do here that's different, I always felt like acids were named backwards. We actually named the polyatomic ion first. So I go and I look at my list of polyatomics for IO3. All right, so let me go look at what IO3 is called. When I look at my list of polyatomics, IO3 is called iodate. All right, so let me write that down. IO3, iodate. Now, when it turns into the acid, right, and we know it's an acid because it's got the H in front, we actually change the 8 to ic, and then we add the word acid. So again, they're named backwards to me. The H is named second by saying acid. The IO3 is named first by saying iodic. So if you notice these two acids, I did them back to back on purpose. When it's binary, we always put hydro. If it's non-binary, we never start with hydro. That is like the big mark to distinguish whether it's binary or non-binary. So if there's only two, hydrogen and a nonmetal, always hydro. More than two, never hydro. So along that note, if I give you these two as options, which one would be bromic acid? Well, if there's no hydro, that means it's not binary. So it can't be HR, it's got to be HBrO3, right? So binary acids always start with hydro. All right, so if it's binary, you're going to always see hydro in the name. This one didn't have hydro, so it can't be the binary acid. It's got to be the other one. All right, H3PO3, another non-binary acid, more than two. So we have to know what is PO3. So I go and look at my list. PO3 -3 is a polyatomic ion that's called phosphite, right? And again, I just know that because it's right there, right? So it's phosphite. So when I go to name this, again, it seems weird. We name the hydrogen second by saying acid. So we named the phosphite first, right? But what we saw is up above, 8 goes to ic and the ite goes to us. Now, instead of just phosphorus acid, it's actually phosphorus acid. And that, I know that's a little tricky. Most of them, they only drop and replace. So 8 goes to ic, ite goes to us. There are only two exceptions to that, and that is phosphorus and sulfur. And I don't fully understand why, because if you think carefully about the rules, when sulfur is binary, we don't say sulfuride, we just say sulfide. We don't say phosphoride, we just say phosphide. So the OR thing is gone. But in the acid case, they bring it back. I feel like they didn't think that one through when they made up the rules. But anyway, they didn't ask me because this was done a long time ago. But ite, drop the ite, replace it with us, and then add the word acid. But just in the case of phosphorus and sulfur, that's when they bring in that extra syllable. So instead of phosphorus, it's technically phosphorus acid. Now, if I look at the next one, this HPO3 -2, what I want to make sure and emphasize here is that that's technically not an acid because it's carrying a charge. When we go through the system of acid nomenclature, these are all compounds with no charge. So that's how we know to name them as an acid. This right here is a polyatomic ion, right? It's a group of atoms that carry a charge. So this right here, this would be called hydrogen phosphite, because we see the PO3 is phosphite and the H would be the hydrogen. So the reason why I ask this is or kind of point this out is that a lot of students want to go back up to this one and say, well, wait a minute, why can't I just say trihydrogen phosphite? Because that's what it is. And the difference is because the H3PO3 has no charge. So it's not a polyatomic ion anymore. So we don't name it like a polyatomic ion like we did for HPO3 -2. This has a charge, so it's a polyatomic. In the H3PO3 case, this is a full-on acid. There's no charge. So that's how we know, oh, okay, we follow the acid nomenclature system. And that tells us that if it's ite, we change it to us and we add the word acid. If it's carrying a charge though, then we have to name it like our polyatomic says, and then that's when we say hydrogen phosphide. Now for this class, we're not going to ever see HPO3 -2 by itself. It would always be partnered with something. So like as an example, you would see it as a compound, CaHPO3, right? And then you would say, okay, this is calcium, hydrogen, phosphide. But what you wouldn't do is say this is calcium phosphite acid or something, you know what I mean? In order for it to be an acid, the H has to be all the way in front. If the H is in the middle, it's not an acid, that's part of the polyatomic ion. All right, so I know that sometimes can be confusing. Nitric acid, all right, again, naming it backwards, acid means we start with H. Nitric, what that means is, if we think about it, there's no hydro. So that is the clue that we're looking for a polyatomic ion, right? If there's no hydro in front, we know it's going to be a polyatomic. And then we have to look at the ending. Ic would have come from 8. So we want to look for nitrate. When I look at nitrate on my list of polyatomic ions, it is NO3 with a -1 charge. So if nitrate is -1, hydrogen's +1, those two charges cancel out. So it would be HNO3. All
Can you
right,
give
so,
us sorry.
no, go ahead.
Do you mind giving us an example where we would have to write it out and the H would have a subscript number?
Sure, like as an acid?
Yeah.
Yeah. Like giving you the name first or giving you the formula first?
The name first, please.
Okay, yep. All right, so sorry to scroll down. Let me go up here. So let's say I've got sulfuric acid. All right, so H for the cation, right? Because that's the acid part. All right, and again, weird because the H is named second. The sulfuric, if we tackle that second, we know that because there's no hydro in the name, we know we have a polyatomic ion. And then we look at the ending. The ic means that the polyatomic ion ended in 8. Right, and as I picked this one to kind of go back to what we were talking about with phosphorus, right? Sulfate becomes sulfuric. It brings back the UR, and phosphite became phosphorus, right? It has that extra sound in it. So sulfuric is just coming from sulfate. And if I look at my list, sulfate is SO4 -2. All right, and again, I'm pulling that not out of nowhere. That's what it is, right? Sulfate means SO4 -2. Because the sulfate is a -2 and hydrogen is a +1, those charges need to cancel out. So I'm going to need 2 hydrogens to balance the sulfate. So sulfuric acid is H2SO4. All right, so acid nomenclature, make sure you still treat it as an ionic compound. The charges still have to cancel out. So if your ion is -2, you need 2 hydrogens. If your ion is -3, you need 3 hydrogens. Because hydrogen is always a +1, it's not too bad, right? Like whatever the charge on the polyatomic is tells you how many hydrogens you need to balance it out. Right? Then what I have at the bottom of the page to finish out what we have to do for today, it's basically a scattering of everything. So it'll help us review how do we recognize what type of compound it is and how to, like, what are the rules? Like, how do things change? So this is kind of, you know, a free for all at the end. So I've got P2O5. So what I always want you to do is when you name it, you go and you look, and you say, oh, okay, phosphorus, my first element, it's a nonmetal. Okay, that means this is not ionic. That means that this is covalent. And what I know about covalent compounds is that this is when I use my prefixes. So for me, I'd be like, yes, this is this is an easy one. I like this one. So I want to say 2-phosphorus. So diphosphorus.
Are you able to tell that it's covalent because it's combination between phosphorus, a metal, and oxygen, a nonmetal?
Phosphorus is a nonmetal. You always, yeah. So that's what you look for. If both elements are to the right of the stair step, so phosphorus and oxygen, that's how you know it's covalent, and that's how you know to use the prefixes.
Okay.
So we say diphosphorus, and then 5 is penta oxide. All right, so diphosphorus pentaoxide. Love those. Don't think about charges. If you did, it would get confusing, because if you think charges, you're like, wait, phosphorus is -3, oxygen's -2. How does that work? It doesn't, because it's not an ionic compound. So there's no charges to worry about. The Fe2O3, now, first thing I do, I look at my periodic table. Fe, iron, transition metal. That makes me think I need to use a Roman numeral. So iron, I'm going to leave a space for that and come back. Now, the second part of this is my endings, right? My last 3 letters, it's going to be either IDE, ITE, or ATE. And since this is just a binary compound, only 2 elements, I always use IDE. All right, so that is a mark of a binary compound, right? So now the only thing I have left to do is figure out the Roman numeral. Oxygen, -2. What I can see is that charge on oxygen is the subscript on the iron. So the opposite will be true. This has to be iron with a +3 charge. So iron 3 oxide. All right, the next one I've got Cr, which is chromium. And if I look at my periodic table, another transition metal, which means, again, I'm going to have to use the Roman numeral. And then the iodine is going to become iodide, because again, it's a binary compound here. Now, iodine, -1. There's 3 of them present, so that must mean that the chromium is carrying a +3 charge. So chromium 3 iodide. So your type 2 metals always, always, always have to have a Roman numeral. All right. The next one we've got is Pb, which is lead. And I gave you 3 different compounds of lead to show you the importance of the last 3 letters. All right, so I'm actually going to start with this one over here, Pb3N4. So lead, we talked about the type 2 metals being the transition metals, but remember we said, well, it's also those metals that are underneath the stair step, right? Transition metals stop here. So lead is one of those type 2 metals that's under the metalloid stair step. So we still need a Roman numeral here. So nitrogen, we know, is a -3, and we know that there's the crisscross that's going to help us here. So this must be lead 4, and because it's binary, it's got to be nitride. So lead 4 nitride. The other 2 compounds here, now these are not binary, so we're not going to have the IDE ending. Now we're going to see 8s and 8s because it's a polyatomic. So I go to my, well, actually, let me start here. I'm going to have lead, Roman numeral, and lead, Roman numeral, right? That's something that all of those compounds have in common. Lead always needs a Roman numeral. Now the NO3, I go and I look, NO3 is a -1 charge and it's called nitrate. So I know here NO3 is called nitrate and it has a -1 charge, but there are 4 of them in the compound, and that must mean that my lead is carrying a +4 charge. So when I name this, it's going to be lead 4 nitrate, right? Lead 4 nitrate. Sorry, that came out like 2. Sorry, that's just 1, right? Lead 4 nitrate. Now in this second compound, we went from NO3 to NO2. And like I mentioned earlier, when you drop one of the oxygens, the ending instead of nitrate is going to be nitrite. And again, it's on your list, so it's not like I'm making up something that's not there. NO2 is called nitrite. It also carries a -1 charge. And also because there are 4 of them in the compound, that means the lead must be a +4 charge. And that's what we put in parentheses. So looking at those 3 compounds, this is why you have to be really careful about the last 3 letters. That's the only thing that changed all the way through. Lead 4, lead 4, lead 4, nitrate, nitrite, nitride. All right. Then the last thing here, we've got compounds that have sulfur. That's sort of the common theme. First one, non-metal carbon, non-metal sulfur, 2 nonmetals. So when you have a nonmetal and a nonmetal, we know it's covalent. We know covalent, those are my favorite. That's where you get to use the prefixes. So CS2 would be carbon disulfide. All right, the Na2S, now we have metal. and nonmetal. So that means this is ionic. So no prefixes, right? Prefixes are not an option. Instead, what we do is we name the metal sodium. And we ask ourselves, whenever we have a metal, do we need the Roman numeral? And with sodium, because it's an alkali metal and it's always +1, the answer is no. So we just say sodium, and then sulfur becomes sulfide. All right, no prefix. Then on the last one, we still have sodium, but now we have metal and a polyatomic ion. So what's different here is going to be the ending. So now this is going to be sodium, SO3. I have to go look for that and figure out SO3 is called sulfite. So when I see that SO3 group, that's what I want to put. I want to say, oh, okay, this is sulfite, not sulfide, but sulfite. So that completes the nomenclature portion of chapter 3. So again, for credit quiz 2, I broke it up. I took part of chapter 2, the structure of the atom, family names, ion charges, and I combined it with the nomenclature part of chapter 3, which is what all of this Zoom session covered today. As I mentioned, if you go into the chapter 2 and 3 folder, there are separate videos on nomenclature. There's a lot of extra stuff there for you to look at. So hopefully you've got plenty to kind of keep you entertained over the next week. And kind of where we all began. The credit quiz for credit quiz 2 is due a week from today at midnight. So next Thursday at 11:59 p.m. So Tuesday, when we come back for the next Zoom session, we're going to finish out the chapter 2 notes and we'll finish out the chapter 3 notes. All right, and we'll take care of all of that stuff. And that'll be the second part. That'll be the credit quiz 3. That won't be due until a week from Tuesday. So there's a lot here, I know. Definitely don't delay getting started on practicing it. Hopefully there's a lot there to keep you busy. If you have any questions for me though, please reach out. If you don't have anything for me today, I will see you back on Tuesday. If you have questions for me though, let me know, but have a good weekend. So credit quiz 1 is in the chapter 1 folder and it is due Tuesday at midnight. It covers credit quiz 1 or chapter 1 material.